Hawking radiation is blackbody radiation that is predicted to be released by black holes, due to quantum effects near the event horizon. It is named after the physicist Stephen Hawking, who provided a theoretical argument for its existence in 1974. Hawking's work helped explain the results of Jacob Bekenstein, who had predicted that black holes should have a finite entropy. Hawking radiation reduces the mass and energy of black holes and is therefore also known as black hole evaporation. Because of this, black holes that do not gain mass through other means are expected to shrink and ultimately vanish. Micro-black holes are predicted to be larger emitters of radiation than larger black holes and should shrink and dissipate faster. In June 2008, NASA launched the Fermi Space Telescope, which is searching for the terminal gamma-ray flashes expected from evaporating primordial black holes. In the event that speculative-large extra-dimension theories are correct, CERN's Large Hadron Collider may be able to create micro-black holes and observe their evaporation. No such micro-black hole has ever been observed at CERN. In September 2010, a signal that is closely related to black hole Hawking radiation, see analog gravity, was claimed to have been observed in a laboratory experiment involving optical light pulses. However, the results remain unverified and .projects have been launched to look for this radiation within the framework of analog gravity. Black holes are sites of attraction. Classically, the gravitation generated by the gravitational singularity inside a black hole is so powerful that nothing, not even electromagnetic radiation, can escape from the black hole. It is yet unknown how gravity can be incorporated into quantum mechanics. Nevertheless, far from the black hole, the gravitational effects can be weak enough for calculations to be reliably performed in the framework of quantum field theory in curved spacetime. Hawking showed that quantum effects allow black holes to emit exact blackbody radiation. The electromagnetic radiation is produced as if emitted by a blackbody with a temperature inversely proportional to the mass of the black hole.Physical insight into the process may be gained by imagining that particle-antiparticle radiation is emitted from just beyond the event horizon. This radiation does not come directly from the black hole itself, but rather is a result of virtual particles being boosted by the black hole's gravitation into becoming real particles. As the particle-antiparticle pair was produced by the black hole's gravitational energy, the escape of one of the particles lowers the mass of the black hole. An alternative view of the process is fluctuations cause a particle's antiparticle pair to appear close to the event horizon of a black hole. One of the pair falls into the black hole while the other escapes. In order to preserve total energy, the particle that fell into the black hole must have had a negative energy, with respect to an observer far away from the black hole. This causes the black hole to lose mass, and, to an outside observer, it would appear that the black hole has just emitted a particle. In another model, the process is a quantum tunneling effect, whereby particle-antiparticle pairs will form from the vacuum, and one will tunnel outside the event horizon. An important difference between the black hole radiation as computed by Hawking and thermal radiation emitted from a black body is that the latter is statistical in nature, and only its average satisfies what is known as Planck's law of blackbody radiation, while the former fits the data better. Thus thermal radiation contains information about the body that emitted it, while Hawking radiation seems to contain no such information, and depends only on the mass, angular momentum, and charge of the black hole, the no-hair theorem. This leads to the black hole information paradox. However, according to the duality, also known as the ADS, CFT correspondence, black holes in certain cases, and perhaps in general, are